general relativity step by step. I've been gradually identifying the terms in this 2x2 matrix here, and now I've just got one single degree of freedom left, which I've called capital D, and that appears here and here. So I need another nice simple case. So what have I done so far? This is the unbarred coordinate system here, and I've shone a laser light leftwards and I've shone a laser light rightwards, and I've used those 2 points there. I've also used this point here, and I've used Einstein's photon clock, bouncing the photon backwards and forwards between two mirrors, that thought experiment, to pin down the different terms in this equation here. So of course this is the one that's left here, which is displaced in distance but not in time. So I'm going to say that T bar x bar equals gamma, just copying from here, beta d, what's this one, beta gamma and d, times 0 and x. Okay, so that tells me that oops, don't know why it does that. That tells me that T bar x bar equals beta dx, yeah, and then it's dx down there, isn't it? Okay, so that's great. So that tells me that delta s squared, which equals minus t squared plus x squared, equals delta s bar squared, which is minus t bar squared plus x bar squared. So let's just go through these guys. That's just going to be x squared, because in this case my t term is 0, so there's no time there, equals minus beta d dx squared from that term there, that's my t bar, plus dx squared. Okay, so what have I got? I've got x squared, this is ds squared, equals minus beta squared d squared x squared plus d squared x squared. So if x is not equal to 0, I can cancel it. 1 equals minus beta squared d squared plus d squared. That tells me that 1 equals d squared, 1 minus beta squared. So that tells me that d squared equals 1 over 1 minus beta squared, and that tells me that d equals 1 over root 1 minus beta squared. There is in fact a sign error, but I'm again going to choose the positive sign. So I've found out what d is. Oh, and that's equal to gamma, of course. So what did I have last time? What did I have last time? I had this thing here. I may as well see if I can write it out in one go. That's gamma, just copying from here, beta d, beta gamma, and d here. So now I'm in a position to write it all in, because now I know that d equals gamma. So we've got gamma, beta gamma here, and gamma there. Let me write the whole thing out. Look how nice that is. T bar x bar equals gamma, beta gamma, gamma, a beautiful symmetric matrix. See how the symmetry of time and space is made obvious. Tx. And that is how to link two coordinate systems, one moving at speed beta relative to the other one. And this is called the Lorentz, no, there's no T in it, Lorentz transform. And this is why special relativity is boring. Well, it's not boring, but if you've got a problem with a twin paradox, or some guy with a pole running into a garage, or some kind of paradox, or some kind of complicated thing in special relativity, it's not complicated. All you've got to do is to transform with the Lorentz transformation matrix here, and you will see what's going on. Quite often when you think of a paradox, it's because you forget or neglect to transform t into t bar using this formula. But now I've got this beautiful, beautiful, beautiful formula, t bar x bar, and this is all you need to know about special relativity. There is nothing else. Relativity, or special relativity at least, is just this. I like it so much, I'm going to write it again. In fact, I'm going to say that I'm going to write it out in its component form. Isn't that beautiful? Isn't that beautiful? This is the relationship between two relatively moving coordinate systems. And I've used nothing, no physics at all in this, except for one fact, which is that the speed of light is the same for all observers. That's it. Oh, I've used the fact that space is isotropic, I think. I think I've used that as well, yes. But I'm not using anything like the first law of thermodynamics here. I'm not using anything like the second law of thermodynamics. I'm not using any of Maxwell's equations. I'm not using anything. All I'm using is just this single observation. The speed of light. It's the same for all observers. There it is. Bing, dong, 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 dong. That's what it looks like to me with my photon bouncing up and down. What does it look like to my mate? Oops, he should be blue. He should be blue. What does it look to my mate in his spaceship? Here he is. Here's my friend in his spaceship. Lum, 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 lum. What does he see? He sees this. He sees the mirror moving backwards because he's going right to left, so the mirror's going left to right. There's the mirror. What does the photon look like to him? The photon looks like this. And everyone sees the photon going at the same speed because the speed of light is the same for all observers. And from that very, 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 very natural, it almost feels like it's too obvious to mention. Of course the speed of light is going to be constant for all observers, but it's not mathematically the case. The Galilean transforms don't have the speed of light being the same for all observers. This is pure physics. This is not a mathematical statement. But from that single observation flows quite complicated reasoning for sure, and it all boils down to this beautiful thing here. Stop. Stop, 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 stop. Beautiful. Look at it. Isn't that beautiful?